Today I'm going to go through balanced and unbalanced forces, which is basically Newton's first two laws of motion. Okay, so here we got situations where the animals are either stationary or moving with constant speed or accelerating. So in the first case, you can see the forward arrow is the same length as the backward arrow. That means it's moving, and because the forces are equal and opposite, it must be moving at constant speed. So the animal is not going to be stationary. They want you to write the animal as either stationary. If it was stationary, there would be no drag force. So I think that's a mistake on this slide. In number 2, the forward arrow is bigger than the backward arrow. That means the bear is accelerating, so the animal is getting faster. And in number 3, the animal is getting slower. It's slowing down because the arrow behind it is larger than the arrow going forward. So you need to decide whether they're faster, slower, or going at constant speed. So one is going faster, accelerating, one is going slower, and the other is going at constant speed. So I need to change the text for number 1, and it should say the animal is moving with constant speed. If it was stationary, there would be no forward force and therefore no drag force. Whenever there's drag force, it's due to motion because it's due to air resistance mostly. Okay? So what about this spaceship? If this spaceship, what forces are acting on it? If it's in space far away from any planets or stars, so any gravitational field will be far away, and it switches its engines off, it must be either stationary or moving with constant velocity. And this is the case which in the previous page, number 1, they got wrong, because you can keep going at constant velocity if there's no air resistance. So once you switch your engines off in this Starship Enterprise, this is from Star Trek, which was a very popular series in the 1960s, where it started, and it's still going today. So that's with the original captain, Captain Kirk, and his science officer, Mr. Spock. So they were going into space. If you're far away from all gravitational effects and you switch your engines on, you will continue to travel at constant velocity. And that's an expression of Newton's first law of motion, which we'll go through in the slides which follow. Which basically says any object will continue at rest or continue to moving with constant velocity unless acted upon by a resultant external force. That means an unbalanced force. Okay? And if I go back to the slide before, number 1, there is no unbalanced force. Number 2, there is an unbalanced force, and number 3, there is an unbalanced force. And the direction of the unbalanced force, in other words, which direction is the force bigger in, is the direction of the acceleration. Okay, so resultant forces is a way of analyzing what's going on when you got more than one force acting on an object. Okay, so with Newton's first law and Newton's second law, we're looking at a single object and analyzing the forces acting on that single object. So a resultant force is a single force that can replace all of the other forces that might be acting on it. Okay, so in this case, it's a person. Okay, can you work out the resultant force for each of the following? Okay, and then draw an arrow to represent the resultant force as a single arrow. Okay, so the person on the left here, he's got 500 newtons pushing to the right, 100 newtons pushing to the left, so the resultant force will be 500 minus 100 to the right, so it'll be 400 newtons to the right. Okay, in this case, the 700 newtons to the right, 600 newtons to the left, so the resultant arrow should be 100 newtons to the right. Okay, and in this one, the up and down arrows are 100 newtons each, so up and down is balanced, so he's not going to move up or down, the force is balanced up and down, but left and right, the left arrow is 800, the right arrow is 700, so the resultant force would be 100 newtons to the left. Okay? So that's what resultant force means. It means the net force when you take into account the magnitude and direction of all of the forces drawn on the object. Okay, so in summary, if an object is stationary and has no resultant force on it, the object will continue to stay stationary. Okay, so if it's not moving and there's no resultant force acting on it, it will continue to stay stationary. Okay, that's an aspect of Newton's first law. Yeah, and then the second statement, if an object is stationary and a resultant force acts on it, the object will accelerate in the direction of the resultant force. Okay, and then number 3, if an object is already moving but no resultant force acts on it, the object will continue to move at the same speed and in the same direction. That's another case of Newton's first law in action, because the forces are balanced on it. So if the forces are balanced on it, it will not change its motion. The velocity will remain the same. Okay, and finally, if an object is already moving and a resultant force acts on the object, it will accelerate in the direction of the resultant force. And if that resultant force is against its motion, the acceleration will be negative. In other words, it will decelerate. So these are summaries of balanced and unbalanced forces, which can be explained by the way Newton explained it. So what are Newton's laws of motion? It is analyzing how to look at a single object and decide what will happen. Certainly, the ones that we've looked at, in cases of balanced forces, it's Newton's first law, and in cases where there are unbalanced forces or a resultant force is acting, then it's Newton's second law. We're not going to go into Newton's third law of motion in this video. That one is slightly different, and it's not just about balanced forces and unbalanced forces. It's what you may have heard of, which is for every action there is an equal and opposite reaction. And with Newton's third law, we're doing it separately because we're not looking at one object in Newton's third law, we're looking at two objects, how they interact. Okay? And there'll be a separate video following this one on Newton's third law of motion. Okay, so first of all, Newton's first law of motion. So Newton lived in the 17th and early 18th centuries, and he was basically regarded as one of the all-time top physicists in history. So he said, a body will remain at rest or continue to move with constant velocity as long as the forces acting on it are balanced. Well, those weren't his exact words, but for GCSE, that's a good way of explaining it. And what I said is Newton's first law is all about balanced forces. And if there are balanced forces, the object will continue its constant state of motion, whatever it is. And so that means its velocity will not change. Remember, velocity has speed and direction in it. And even if its velocity was 0, then it will be balanced, and balanced forces are acting on that object. It still has constant velocity. It's just, in this case, the velocity is 0. So here you got Newton driving a car, which was way before cars were invented, but bear with me. Okay, if an unbalanced force will make me accelerate, he's saying an unbalanced force will make me accelerate. So now he's saying, okay, Newton's first law is about balanced forces. If we have an unbalanced force situation, there will be a resultant force, and that will make me accelerate. He means the car. So if something is pushing the car forward, like this engine, thrust, yes, the car will suddenly start moving, okay? And it shouldn't come to change its motion until there is another force acting against its motion, okay? And an unbalanced force will also make him slow down, okay? So if you have a drag force, for example, in a car, if you take your foot off the accelerator pedal and you just let the car slow down on its own, it's because there is air resistance which will slow it down, okay? And a bit of friction, of course. Okay, so that's balanced forces, and moving into unbalanced forces, which was the example Newton was giving with the car. To make it start moving, you need a thrust or an engine force pushing it forward, and to make it slow down, you need a slowing force, a force acting against this motion, like the brakes or air resistance. Okay, so this is how he worded, or how it can be worded for Newton's second law of motion for a GCSE student. The acceleration of a body is proportional to the resultant force causing its acceleration, and the acceleration will be in the same direction as the resultant force. Okay? So, in other words, if you want to know the size of the acceleration, you can use Newton's second law mathematically, which is force equals mass times acceleration. And the acceleration, of course, will be affected by the mass of the object. For example, if you have a larger mass and the same force, it will be more difficult to accelerate the larger mass, because it's more difficult to move a larger mass than a smaller mass. Okay? So if the mass is large, the acceleration will be small for the same size force. And you can put this in a triangle where F is in newtons, M must be in kilograms, and A will be in meters per second squared. Okay? So make sure you got notes on all this, and I think there is another video which explains all the equations. If you look in the playlist for GCSE, you'll find all the other videos. Okay, so now force and acceleration. If the forces acting on an object are unbalanced, then the object will accelerate like these two sumo wrestlers. Okay, you can see the guy with purple is pushing the guy with blue, and the blue is becoming unbalanced and is moving backwards, because he will move backwards because the force on him is greater than his force on the guy with the purple trunks, or whatever you call what they're wearing. Okay, so once you know the difference in the size of those two forces, you take away the small arrow from the big arrow, and that is the resultant force you use in this equation. Yeah, and you would look at one object at a time. So you would probably look at the sumo wrestler in blue and know his mass, and then you can work out his acceleration. Okay, same equation in triangle form to help you change the subject of the formula. Okay, now you do need to learn this equation. Currently, they're not giving all the equations. However, there is a rumor that they are going to give more equations than they did previously, like before COVID. Okay, so here's some questions you can try on your own. So number one, it says a force of 1,000 newtons is applied to push a mass of 500 kilograms. How fast does it accelerate? Well, so you want to work out A. So A would be, if you cover the A, it would be F divided by M. F is in newtons, so that's 1,000 newtons, divided by M, which is in kilograms. Divide the 1,000 by 500, and you'll get the rate of acceleration, which will be 2. And then you need to know that units for acceleration are 2 meters per second squared. And there's the first answer. See if you can do number 3. Yeah? Stop the video if you want to, and the answer is going to come up in a second. So this time, for number 2, you need to work out mass. So you've got to work out that mass is force divided by acceleration. The force is given to you. The acceleration is given to you. You divide the 3,000 by the 1.5. And if you don't want to see the answer, press pause, and you'll see you can work out the mass of the car as being 2,000 kilograms. Same for number 3. If you want to pause the video, try and do it on your own, you can. If you pause it now, you won't hear what I'm going to say, and then you won't see the answer until you've done it. For number 3, they're giving you the rate of acceleration, so you know A, you know M, they're giving you the weight as being 500 kilograms, and they want to know what is the resultant driving force which the engine is applying when taking into consideration any air resistance. So really they should say, what is the resultant forward force. Yeah, so it's not just necessarily the engine force, because if it's moving there will also be some drag force. But if you take them as if their air resistance can be ignored, then you multiply the mass by the acceleration, 500 times 5, and you'll get the answer showing on the screen now. Okay. Number 4, the same. I'm not going to read it out to you, but you've been given two of the quantities in the equation, and you've got to work out the third, in this case acceleration. If you've done it correctly, you'll see the answer now. Okay, so that's using the equation mathematically for Newton's second law of motion. Okay, now this is, remember, force and velocity have size and direction, whereas some quantities only have size and they have no direction. And this is a quick revision of knowing which quantities in physics are vector quantities, having both size and direction. Another scientific word for size is magnitude, and which quantities in physics do not have any direction. So number 1, mass, has no direction. Number 2, distance is just how many meters you've traveled. It doesn't matter which direction. You could be going round in a circle and you travel the circumference of a circle and you come back to the same starting point, but you've still traveled that distance. Number 3 is acceleration. Well, the acceleration is, as we explained to you in Newton's second law, in the same direction always as the resultant force acting on an object, and therefore it always has an equivalent direction. Number 4, speed is just how fast you're moving, whereas number 5, velocity, also you must give the direction of the velocity. Remember, all vector quantities can be represented by an arrow. Okay. Number 6, energy is just how much quantity of energy is stored in something, due to the energy stores topic that you will study in GCSE. And number 7, time always goes forward. Note, we're not taking into consideration whether time travel is possible into the past. So time has a forward arrow only, forward direction only, so it doesn't have different directions. Number 8, power is energy divided by time, and number 9 is force. Can you think of any other vector quantities that you may have come across in your studies? I can think of one. There is a vector quantity for distance, which they haven't put on this slide, and the vector quantity for distance is called displacement. Okay, so if you walk around in a circle, the distance is the circumference of the circle. Your displacement is actually 0 because it's the difference between your finishing point and your starting point, and that can be represented by an arrow. Okay, usually. The other one that you could think of as having a vector quantity would be momentum. Okay, momentum is any moving object. It has a velocity, so you need to consider whether its velocity is positive or negative, or in whichever direction it's moving in. Okay, so that's a quick revision of scalars and vectors, and here's a special case of the difference between speed and velocity when you have circular motion. So speed is simply how fast you're traveling, so it's a scalar, whereas so this car will be traveling at 20 meters per second. If they only give you the quantity, the magnitude, it's a speed. If they tell you that the car is traveling east at a rate of 20 meters per second, then it would be a velocity. Okay. So, for example, a car traveling 20 meters per second west on the same road, on the opposite side of the road, the difference in velocity between two cars, can you work out what it is? Well, it would be 40 meters per second, because one is going 20 meters per second east, the other is moving 20 meters per second west, so they're actually moving apart at 40 meters per second. Okay? And circular motion is what I wanted to talk about. So if you've got a car going round in a circle, is it traveling at constant speed? Well, usually planets going around the sun, or the moon going around the earth, travel more or less at constant speed, But are objects going round in a circle traveling at constant velocity? The answer is no, they're not, because a car traveling at constant velocity would not be changing direction. So it could be traveling at constant speed, but not at constant velocity. Okay? So if it's not traveling at constant velocity, that means there must be an unbalanced force acting on it. So this is a special case of acceleration at constant speed, and circular motion is something you will study when you look at planetary motion in astrophysics in Unit 8 of the IGCSE course for Edexcel. That's the course that I'm preparing my students for. But it'll be similar in other syllabuses as well. Okay, so thanks for watching. I'll upload this onto YouTube for you. Don't forget to like, share, and subscribe to show your appreciation for all the work that goes into making each video. Even if you get one thing out of it, we do appreciate that any students who come back and listen to more. If you're subscribed, you will be notified when the next video has been uploaded. Okay, so it does really help us, because the YouTube algorithms work by how much interaction you get with your audience. Okay, that's it for now. Hopefully see you in the next video.